Everybody. My name is Anthony Oswega. First of all, thank you for welcoming me here. Something of a reformed physicist. Now that I see you guys have this nice bunker down here, it's kind of making me want to reconsider that. I'm currently a dual degree candidate here at the Yale Jackson School of Global Affairs and the Yale School of Management. And I'm also a program coordinator at the Kimball Smith series. So this NPA talk is brought to you by Wright Lab, Kimball Smith, by viewers like you. So just a bit about Kimball Smith. Seek to create a sort of interaction of science and policy. And hopefully by doing that, both sides of that coin come out better for it. Yeah, and we can think of really nobody better than our guest speaker today, Rachel Carr, who embodies that spirit. And I'm going to read most of this because I will mess it up otherwise. Rachel is an assistant professor of physics at the United States Naval Academy. Previously, she was a postdoc at MIT as a Pappalardo Fellow and a Stanton Fellow for working on neutrino and dark matter experiments, as well as arm control projects. She completed, well, before that, she was an American Institute of Physics Congressional Science Fellow in the office of Senator Dianne Feinstein. And finally, she completed her PhD at Columbia and her BA in physics and philosophy at the University of Virginia. But yeah, let's give it up to Rachel, and thank you for the whole.
Well, thanks so much for having me here. I feel like every time I get to visit Wright Lab, I'm really impressed, not just by like the really beautiful scientific facilities, but by how there are artists and residents here. Yeah, just participation in all kinds of interdisciplinary activities. It's really impressive. So it's been great to learn about the Kimball Smith series, and yeah, it's great to be a part of this. So thanks for having me here today. I should say before I really get started that what I'll show you reflects on a lot of collaborations, particularly with Tony Kendallay at Lawrence Livermore and Bernadette Cogswell and Patrick Huber at Virginia Tech. And then we've already talked a little bit about the mobile anti-neutrino demonstrator collaboration. You see a lot of us here. I'll speak a little bit more about the MAD project, really just towards the end of this. Oh, and I see we've got another MAD collaboration member here, probably a picture here, yeah. All right, but to start at the beginning, so the idea that neutrinos might have some practical utility in nuclear security is an idea with actually a pretty long history. And I'd like to start by telling you just a little bit about that history because it highlights some of the basic points that make neutrinos interesting in this context. And it also highlights what you could think of as like the fundamental tension for making neutrinos useful for anything. And then I will talk about not all, but just some of the possibilities that people have imagined in the past few decades for particular use cases for neutrinos. You see a few of them pictured here, thinking about taking a neutrino detector to a nuclear reactor site where plutonium might be being produced for a weapons program, or various monitoring tasks to do with nuclear fueled submarines, and there'll be a few others. And I've kind of divided these into two categories. First, remote possibilities. I mean remote in two senses. They're, I think you'll come to agree, more sort of speculative, a little bit harder to see actually come into fruition. And relatedly, they involve longer distances between the neutrino source, the reactor or fission source, and the detector. And then I'll present kind of variation on each one of those that I see as being a little bit closer to something that could be real and involves correspondingly shorter distances between the source and the detector. And then I'll end with just a little bit about the technology development that we're engaged in, including with people here at Wright Lab to try to make some of those possibilities more realistic options for policymakers. Okay, to start with a little background. I'm curious, actually, some of you who are in neutrino physics, which is a lot of you, may be familiar with this paper. It's often cited as like the first paper proposing the practical use of neutrinos. It was from 1978 from a group working in, at that time, the Soviet Union. The site of the experiment is the Rovno experiment is in present-day Ukraine. And they were really physicists, and like you guys, they were trying to do basic physics at that time, like very early neutrino oscillation experiments. So they had a neutrino detector that was on the cubic meter scale, and a very convenient source of neutrinos was a reactor, because reactors, as you know, are very bright sources of neutrinos. They're in a steady state, like the brightest sources we have on Earth. And as a scientist, it's nice because you don't have to pay for the source, you just bring your detector relatively close. They were actually under the reactor in this case. And the neutrinos created in the core just stream out of the core, out of the containment vessel, the containment structure, through the Earth, whatever is between you and the detector. I mean, you guys as neutrino physicists know this well. And so this group was really interested in studying the basic properties of neutrinos, but they recognized you could turn the problem around and use neutrinos to study the reactor, or to understand whether the reactor is operating according to an expected civilian power generating profile, and to keep track of the fuel content of the reactor, particularly whether the expected amount of plutonium that breathes in over a cycle in a low enriched uranium reactor was, there in the reactor, or anomalously not present. So this was around the time, it was in the first decade, that the Non-Proliferation Treaty, the NPT, was entering force. So this is the treaty that most countries are a member of. It recognizes the nuclear weapon states that existed at that time and gives them certain obligations. And then the non-nuclear weapon states that are parties to this treaty are obligated not to pursue nuclear weapons. And the kind of verification mechanism for that is the system of safeguards that the International Atomic Energy Agency, the IAEA, has set up over the years. So at reactors, if you're in a non-nuclear weapon state, the IAEA is conducting inspections of the reactor and placing seals on spent fuel as it comes out of the reactor and checking those regularly. There are cameras that watch the refueling process to make sure that plutonium, which could be made into a weapon, is not being diverted from the stream. So what these guys realize is, well, neutrino detectors could be a tool in that kind of regime because they can give you a sense of what's going on in the reactor. You don't even have to go in the reactor building. So it's kind of an interesting, non-invasive possibility that they described. And I guess I could say a little bit more about exactly how this works. So we have a sense that many of you will already know this, since I think there's already here.
I think there might be some non.
Yeah, well, I can just say briefly. So yeah, I mean, from the reactor operator's perspective, the point of the reactor, the real moneymaker, is the fission reaction, where you're splitting uranium or plutonium nucleus. And that doesn't itself produce neutrinos, but the products of fission are these neutron-rich nuclei, and they beta decay a number of times, and each one of those decays produces a neutrino, technically an anti-neutrino, but I'll just say neutrino. And there are, of course, tons and tons of fissions happening all the time in an operating reactor, so you get about 10 to the 21 antineutrinos per second just streaming out of the reactor core. Their rate of emission is proportional to the power of the reactor, and it also has to do with the particular isotopes that are fissioning in the core. So mainly that's uranium-235, plutonium-239. And I don't know if you can really see in this plot, but this one makes it a little more clear. If you area normalize these, the energy spectra coming from the individual isotopes is different. So you can see the plutonium isotopes, the blue and the black, have a softer, lower energy spectrum than the uranium ones. So if you observe a combination of the neutrino rate, energy spectrum, and a neutrino detector, you can figure out what's going on in the reactor core, basically the power level and the fuel content evolution over time. And this has actually been done in many experiments now, just actually kind of as a part of basic science experiments. And I'll very briefly describe how the neutrinos are actually detected in these cases. In the vast majority of reactor neutrino detections so far, and pretty much all the ones I'll talk about in this talk, the interaction channel used is inverse beta decay. So an incoming antineutrino, I guess represented by this wave, interacts with a proton, and you get a neutron and a positron out, which can be detected. Don't be like misled by this cartoon. They don't preserve the direction of the incoming neutrino that nicely. It would be nice if you could just point back to the source, but the neutron kind of wanders around before it's visible. The positron actually scatters weakly backwards. So yeah, you see that a neutrino interacted and what energy it had, but not necessarily where it came from. There is a reaction that would give good pointing information when a neutrino scatters off an atomic electron. The electron does preserve the momentum of the neutrino. This has been observed at reactors, actually first at reactors, but it has a cross-section that's about 15 times lower than IBD in the relevant energy range. And the backgrounds for a single electron, as you can imagine, are like way higher than this nice double, this coincidence signal. So I'll maybe make one brief mention of neutrino electron scattering later, but it's not the main channel we're looking at. And then of more recent interest, it would be nice to detect reactor neutrinos via coherent elastic neutrino nucleus scattering of sevens, because as you know, this is a coherent interaction with the whole nucleus. So you get this enhancement with the number of neutrons squared. So that can be like factors of hundreds. But the energy deposit is really small, so it requires very low thresholds and low backgrounds. And I mean, there's one claim of an observation of sevens at a reactor source, but it's sort of controversial and definitely still something that people are trying to get a clear handle on. So this isn't a science talk, but I guess there's the map sort of disappeared. You can imagine this superimposed on a map of the world. Maybe you can see a little bit over here. Yeah, so I just wanted to give a sense of how active reactor neutrino physics as like an experimental science still is. There are many collaborations using reactors as sources for science measurements worldwide, or planning to, including some familiar to you guys. And I'll just point out a few of these to give a sense of scale for what neutrino detectors can range over. Again, this is somewhat geared at maybe an audience that is not totally familiar with neutrinos. So, but I'll get onto some stuff that'll be novel to those of you who are familiar soon. The largest of the projects shown here is the Juno experiment in southern China, which, does anyone know, is it taking data quite yet? It must be very soon if basically the construction was happening last year. So this is a picture of that detector under construction. You can see people on it. It's about 35 meters across. It's 50 kilometers from a set of 10 power reactors. So it's looking at a huge, bright reactor neutrino source, 30 gigawatts total reactor power. And it's also a huge detector. It's 20 kilotons of liquid simulator. On the other end of things is a detector well known to many folks here because it's built here at Wright Lab, the Prospect detector, which you can see is much more human scale. And it was deployed only 8 meters from a research reactor, so a relatively small reactor. And it's just about 4 tons total mass and only like 1 ton by usual. So, a huge range of detector sizes in play here. And I mean, you can see that's just a nice illustration of the inverse square scaling of the neutrino flux. As you get farther away from a reactor, the flux goes down as distance squared. So your detector volume has to go up at least as distance squared if you want to detect the same number of events, and probably more because your backgrounds are also in scale with detector size. I mean, I know inverse scale laws are like one of the first things we learn in physics, but it's still surprising to me to see how big these detectors get, how fast. 50 kilometers is within the same, kind of county as the both the detector and the source. So those really aren't that far away. All right, well, before I move on to talking about how detectors at various scales might be used in nuclear security applications, I want to make one more historical point. Actually, I only learned kind of recently that 1978 paper from the group working in the Soviet Union, well, it might be the first case in the open literature of a discussion of neutrino applications, but it's certainly not the first time people thought about it. Bruno Pontecorvo during World War II was at least at one point working in Canada. And as you know, at that time, neutrinos had been hypothesized, but they weren't detected for another decade or so. But he was thinking about whether they could be detected and wrote this internal report, kind of anticipating the radiochemical methods that were used by Ray Davis later. And this report got classified. This whole story came up in the research that Frank Close did for his biography of Pontecorvo. So yeah, he found this report that was classified for some time, and his understanding was that the reason it got classified was because Canadian authorities recognized that if you could detect neutrinos, you could perhaps track nuclear-fueled submarines as they were moving through the ocean. There weren't even nuclear submarines yet for some years, but the idea was certainly in people's minds since Fermi's first successful reactor experiments. So this is interesting history, and another point here that I think will strike today's neutrino physicists as sort of amusing is that Pontecorvo kind of mentioned that, yeah, in principle you could detect neutrinos, but your detector have to be very large, on the order of cubic meters. So the material would have to be cheap, which is funny to think of now that we have now tens of thousands of cubic meters in some neutrino detectors. But I think he presciently was concerned about how things would scale, and that really is kind of one of the fundamental limitations for applications of neutrinos. But of course, it's like the flip side of what makes neutrinos interesting for applications. So I really like how this kind of fundamental tension was posed by the Jason Defense Advisory Group in a report on neutrinos. They said, yeah, for any application you can imagine, neutrinos have this great advantage. They interact weakly with matter, so they can pass through any shielding, the Earth. Then they have the great disadvantage that they interact weakly with matter, the exact same thing. So, it's hard to actually detect them. And somehow this is just the upside and downside of the fundamental nature of the weak interaction. And I think if we are going to find actual practical niches for neutrinos, it's a matter of sort of balancing the upside and downside of this and finding like a sweet spot where you're getting the benefit, but you're not like throwing it all away by requiring an enormous detector. So with that said, let me actually next describe some use cases that would require pretty large detectors. I think they're not totally out of the question for the future, and they kind of introduce some ideas that then I think are more practically approached on the smaller scale. So we'll talk about the possibility of looking at reactors around the world from long range, the possibility that the thing that got Pontecorvo's earlier work classified, possibility of tracking submarines, and then also the potential for looking at nuclear weapons tests worldwide using neutrinos. And I'll start with reactors, just terrestrial reactors. Again, the interest here would be that reactors are a place to produce plutonium for nuclear weapons. But the ability to see neutrinos from nuclear reactors at long range actually is demonstrated. The Camland experiment, for one, did this. So just to remind you, Camland is in central Japan, it's tens to hundreds of kilometers from, well, in decades past, there were over 50 operating reactors mostly around the coast of Japan. And so CAMLAB is making an oscillation measurement using those reactor sources. But it's interesting to look at just their total event rate over time. So the black is CAMLAB data superimposed on their predictions for neutrino events. Is that
Just someone doing.
okay? Great. And you can see that, yeah, so the data is tracking some variation in expected power over time, but that becomes really obvious in 2011, which is perhaps not surprising. But yeah, this is when there was the major earthquake in Japan, the Fukushima disaster, and essentially all of their reactors shut down. So that's quite apparent at long range in this data. And you can imagine kind of flipping the timeline and saying, well, if you had no signal for a while and then a sudden jump up, that would tell you that reactors were turning on. And that has been since observed that some of them have turned back on. So this is kind of a proof of principle for observing the turn on of perhaps an unknown reactor somewhere far away just by observing its neutrino emission. In principle, it sure can be done. But I mean, we got to remember this is a case where this is the cumulative signal of about 50 reactors, the relatively large power reactors. And they're all in the same country as the detector. So this really isn't kind of a true proof of principle of looking far away for a single, often small plutonium production reactor. I think to see how viable or not that is, it's more useful to look at cases a little more similar to that. And there are plenty of case studies about long-range reactor monitoring over the years, but a lot of them are kind of, particularly tailored situations where parameters are picked to kind of work. So we thought it would be interesting, and just recently did this, to look at the actual set of reactors that have produced plutonium for weapons programs in the past. And interestingly, you can get what seems like a pretty comprehensive set from the open literature, the specific reactors where plutonium was produced for the 9 nuclear weapon states that there are today. So we looked at these 64 reactors spread over 17 facilities in these 9 countries. And you can figure out like where each one of them is and how far it is. So if you look up here, this is the spread in, see over here, the spread in power of those reactors. They're ranging from just tens of megawatts up to, some of them were like dual power and plutonium production reactors. So those can be in the gigawatt range. And we looked at both how far they are from the nearest international border. So that's the span of distances up here, on average 225 kilometers. And then I'll say more about this later, but we also looked at how far each of the reactors is from just the border of the facility that it's on, which becomes relevant if you want to think about cooperative monitoring. But focusing on just this idea of seeing the turn on of a reactor in some other country without the cooperation of that country using a neutrino detector, you can ask how large a detector does it take in each one of those cases. And so we ran this calculation assuming inverse beta decay signal. And okay, I'll talk about the cooperative cases later, but focusing just on the beyond border cases, we figured that probably the most realistic detector technology there is gadolinium doped water, like Spray is now using. So if you use kind of the super K basis to scale from and assume a 1% systematic on all backgrounds, which is pretty optimistic, you find that again, we'll save these for later, but then in this beyond border monitoring regime, to be able to see the actual plutonium production sites around the world, you'd need detectors, at least a kiloton in some kind of lucky cases, but generally more like 100 kiloton scale. So perhaps it's not surprising, but I think it's nice to get some like kind of concrete image in your mind of what would actually have been required in these actual historical cases. I mean, you can see things kind of vary. It happens that Dimona site in Israel is pretty close to the border with Jordan, and Sellafield in the UK is kind of close to a coast. I should say the brown circles are cases where the reactor is closest to a land border. The blue are cases where you're closest to an ocean border, so you're thinking of underwater deployment. And yeah, this is plotting the distance from that reactor to where you can imagine putting a detector, so like the closest international approach point, which is probably not, in most of these cases, a realistic deployment point, but it gives you kind of a minimum possible detector size. And then the size of the points there, those are proportional to the total reactor power at the facility. So Hanford is the big one, where there were a bunch of reactors. But I could possibly look at this for a little while. We're going to explain all the elements again. I'll come to these later. One thing I'll say is, I mentioned there were 17 facilities in this data set. You only see like 8 here. The other ones are not visible in any finite detector size because of the 1% systematic assumed on the backgrounds. That's bigger than the size of the signal, actually. So you would never be able to, if this is true, see those reactors in basically half the cases. And I'll also point out that the way that we were able to do this analysis was looking at just like openly available satellite images of these sites. So even if you were interested in building a neutrino detector at those scales, you can say, I mean, really, we should compare to what other modes of information are available. And you can just on Google Earth find, if you know where you're looking, you know, find very clearly these reactor sites. So I think the bottom line is trying to think about beyond border monitoring of reactors with neutrinos, whether that's still possible, requires kind of forbiddingly large detectors, and sometimes isn't even possible, even in an optimistic background space. Let me pause there for a second and see if the information here is making sense. There's a lot more detail that we could go into. And I'll say this is work that should be on archive soon. Feels.
So the size of the circles that represent the power while they were running.
Yes, if all the reactors at the site were operating at the same time, which they may not have been, but it's
Stored waste on site or something, or did you worry about that?
I mean, so there is neutrino emission from that, but much lower, like many orders of magnitude lower. Yeah. Okay, so this is for terrestrial reactors. They're at a fixed location on the Earth. But I think you already kind of have a sense here of what it's going to look like if you try to think about moving reactors, like submarine reactors. And yeah, well, one statement is that report of Pontecorvo's that got classified was not long after that declassified, because I think people, once they started to really work the numbers, recognize, yeah, this is actually not something to be super worried about. Nonetheless, people have come back to that idea of tracking submarines using their neutrino emissions many times. One interesting example was in the 1980s, actually a couple of different groups approached the US Navy with ideas, including Joseph Weber, who happened to have been an undergraduate at the Naval Academy. Not at that time, but previously. And so, yeah, he served on submarines and knew the Navy. And what he suggested was, knowing that there was a rate issue, maybe you could greatly increase the cross-section of neutrino interactions, even beyond the coherent scattering that we know about, by a kind of super coherent interaction where a neutrino scatters coherently off an entire crystal. And he built these sapphire crystal detectors, which were supposed to be capable of detecting reactor neutrinos, and would have been a huge deal that, you know, that they would have actually really been a game changer for submarine tracking if they'd worked. This is not one of them, actually. This is another thing that Joseph Weber is well known for. You may know, yeah, it was not. So he also did some work on gravitational wave detection with a system that also turned out didn't work, but it was, you know, I think helps get people thinking about experimentally detecting gravitational waves. Anyway, the Jason group, so these are physicists who do various studies for the Department of Defense, looked at Weber's proposal, one from Raytheon and others at that time, and they wrote actually a really great report. This is what that earlier thing I quoted about the advantage and disadvantage comes from. It's a really nicely written report that's publicly available. They concluded that even if you had an ideal sevens detector, so like 100% efficient, zero backgrounds, you know, pretty large nucleus, you still couldn't beat the performance of sonar that was available in the 80s in terms of like if you're instrumenting a detector or in a volume of seawater, how many detectors does it take, and you know how well can you see things. And it seems like the game on that hasn't really changed because that's even well beyond what's experimentally achievable. So this seems to be, I mean, I think for the foreseeable future, not really a possibility or a concern. But there are other things you could think about doing with submarines. Somewhat easier than seeing the signal from a submarine reactor is trying to communicate with the reactor. Actually, it's not that much easier with conventional techniques. Like radio doesn't penetrate seawater very well. Only very, very low frequencies can send a signal, so they have low like bit rates. But for a while, people have recognized, well, if you had a steerable neutrino beam, you could, in principle, shine that at your, if you knew where your sub is supposed to be, shine it there and send some message. This idea was revisited by Patrick Huber in 2010, and it was interesting at that time that if you took the expected neutrino flux from a muon storage ring, so, you know, I think people would consider now are considering building, and you just kind of had the submarine surrounded by and like towing along some simulator panels, you could actually improve upon the data rate that's possible with very low frequency radar or radio. But here, clearly the challenge is also great, particularly on the source side, because you're thinking about building this enormously powerful steerable neutrino beam, which of course could be intercepted, observed by others. Nonetheless, this is an idea that's patented. It's interesting if you've never looked through Google patents for neutrino ideas. There are some interesting ones. Yeah, so this probably also is an extremely remote possibility. One more source that might be considered for long-range observation, and is actually kind of the closest to being feasible, is looking for nuclear explosions, namely nuclear weapons tests occurring worldwide. And I mean, the advantage with what makes it easier to see a nuclear explosion versus a reactor is what was recognized immediately by Fred Reinus when he was thinking about making the first neutrino detection back in the 50s. I mean, as many of you will know, the first proposal for detecting the first neutrino was to go to a nuclear test in Nevada and be, you know, relatively close, say 40 meters from it. Somehow you have to isolate the detector from the shock wave of the blast. But if you could do that, it would be a convenient signal because as in a reactor, neutrinos are coming from the decay of fission fragments. But the fission fragments are all created at like, you know, within less than a millisecond. And so most of them are pretty short-lived, and most of the neutrinos are emitted pretty soon after the actual explosion. We modeled this, and it seems like about 60% of the neutrinos above inverse beta decay threshold would come in the first 10 seconds after nuclear explosion. So you're only looking at 10 seconds of data, so the backgrounds are vastly reduced just by that like time dating. And although this experiment wasn't done, and as far as we know, neutrinos haven't been detected from any of the 2000 plus nuclear tests since this time, people have come back to this idea now and then. In particular, in the early 2000s, when the Comprehensive Test Ban Treaty was open for signatures, it's still not in force. The US and enough other countries haven't ratified it. But anyway, they started building up the verification system for that treaty, which is based on many detectors throughout the world. Seismic detectors are kind of the most sensitive part. There's also infrasound detectors and water and radionuclide stations and so on. And people have asked, well, could neutrino detectors help with that global system? Because in principle, you could see neutrinos from an explosion that might be below the threshold of the rest of the sensors. But actually, the seismic sensors are very good, and they cover most of the world with like sub-kiloton yield thresholds, which would get pretty much any sizable nuclear test. So probably neutrino detectors couldn't be helping for that. The one other possibility that we've looked at is, okay, if a seismic event is registered, you may have a good sense that that was a nuclear explosion, but it could be an earthquake. Really, there's only ambiguity in kind of a small number of cases. Probably a seismic event coming from the North Korean nuclear test site is not, actually that ambiguous. And yet, from like the standpoint of kind of international agencies, I think having additional concrete data can be quite helpful. So we looked at whether you could, with kind of a seismic queuing, meaning like when to look for neutrinos and where they should be coming from. Can you find neutrinos that would be significant enough in number to let you identify that event as, yes, something that included fission? By the way, you don't get neutrinos from the type of fusion reactions in a fusion device, but there's historically always been a fission component of fusion devices as well. So what we show here is as a function of distance from the explosion to the detector for different explosion yields, ranging from pretty small to like pretty big as these things go. How large a detector would you need against an IBD detector, gadolinium doped water? And what you find is that, so if you look at, say, the largest nuclear test that North Korea has conducted, which was about, people estimate about 200 or so kilotons. If you had at that time the Hypercameo-Conde experiment built, which is a few hundred kilotons of volume, it's about 900 kilometers from the North Korean site and happen to be in the same general area. Yeah, you actually probably could identify that explosion was nuclear in nature. But that's a bit of an accident that there happens to be the largest detector, neutrino detector in the world other than IceCube located kind of in this region. I think, again, it's difficult to imagine kind of a purpose-built network of detectors doing something like this. So all that said, I think you can see that, at least to me, any of these long-range possibilities are pretty severely constraining when compared with existing technologies. Just the disadvantages of neutrinos kind of outweigh any advantages. But I'd like to spend a little time on some variations on each one of those cases where we shrink the detector to source distance and go into a really cooperative regime. So it's no longer like surveillance of activities halfway around the world. It's a confidence building, voluntary kind of agreement. I think there are actually some real possibilities for neutrinos there. Okay, so let me say a little about each of these. So coming back to this plot, so we've already talked about the beyond border cases, but we also took a look at each one of the 64 historical plutonium production reactors. And just from looking at images, figured out how far each one is from kind of the outer border of its facility, which is pretty clear when you look at images. And then we asked, what size detector would you need if you were trying to observe that reactor? And observe means see that it's operating in the time it would take the reactor to produce about 1 weapon's worth of plutonium. So we took that as kind of a reasonable time scale. Yeah, how big a detector would you need? This is assuming prospect characteristics, so scintillator with kind of backgrounds that are almost 1-to-1 with signal at close range. So it's not a very, I mean, it's we'll say a demonstrated case. Yeah, so to observe these facilities in that kind of cooperative, you're allowing the detector to be there, but you're maintaining control over your whole facility. In that regime, you find that, unsurprisingly, the detector sizes are much smaller. This is the green. In fact, they're kind of on the scale you could imagine transporting on a truck, which brings to mind that image you saw at the beginning. Almost all of these facilities could be monitored in that kind of cooperative but still significant standoff pattern with a mobile detector. The exceptions here are, it turns out that the reactor facilities in Pakistan have large facility boundaries. The orange here, so each of these green points is connected to an orange point. And that's showing how much you would gain if you could continue to reduce the backgrounds in the neutrino detector. That allows you to get by with a much smaller mass. You can see everything drops into the road mobile category, and you get cases where you don't even need a single ton of detector mass. So I think that's pretty impressive that from outside of the facility, if we were able to reduce backgrounds by a factor of about 100, you could, with almost a person mobile system, provide some confidence that a reactor either wasn't on or was only on in the way you expected. Anyway, I still think that that's not like a natural way to monitor most of the reactors in the world. The reactors in non-nuclear weapon states, as I said, already have these IAEA safeguards inspection regimes set up, which really operate on a pretty shoestring budget. And they seem to operate to the IAEA's general satisfaction right now. So it's not a great argument for introducing a few $1,000 neutrino detector, except in certain very special cases where you might imagine that ability to be outside the reactor facility, like not going in the buildings at all, would be especially valued. Or situations where the neutrino detector itself, like the fact that you can do kind of interesting physics with neutrinos, where those things might make it worthwhile to take this kind of exotic solution and apply it. So we had that idea in mind a few years back. You'll remember this. In around 2018, like the middle of the Trump administration, there was suddenly, you'll remember this unexpected opening in diplomatic relationships with North Korea, where like all of a sudden there were talks between leaders of the US and North Korea. And we were really taken at that time by an op-ed by Sam Nunn and Richard Lugar, who had done a lot of work with the dissolution of the Soviet Union and ensuring the safety of Soviet nuclear facilities at that time. And what they wrote was that to imagine a good outcome on the Korean Peninsula requires unconventional thinking and steps much broader than denuclearization. So, maybe you start thinking about the exotic solutions. And they went on to say that the cooperative threat reduction program that they sponsored in the former Soviet states not only secured the sites and the materials, but it provided connections for the weapons scientists to peaceful scientific work. And they suggested this is a critical component of any effort to dismantle North Korea's nuclear program. So maybe this suggests, if your imagination is open to it, a place where a neutrino detector might be actually kind of well suited. So Just taking a brief look at North Korea's reactor site. This is one of the dots on the previous plots. So they've produced in the past, we think, the plutonium for their nuclear weapons in this 5 megawatt reactor. There's another reactor which was not then operating, now apparently is on the site. And this one's supposedly for just nuclear production, not plutonium production. Probably if there ever is some kind of comprehensive nuclear agreement with North Korea, it would involve the shutdown of this reactor, which is in any case, probably towards the end of its useful lifetime. And this one, if not shut down, would be under quite stringent safeguards to make sure it really is operating just for power production. So we thought, well, it's interesting to look at what you can do with a neutrino detector as an option for monitoring those things. Again, there are easier ways to monitor that a reactor is off or monitoring in an allowed way, but they require you to kind of have access to the building, have people there for inspections. So this is an option which, in fact, North Korea has a history of kind of being resistant to having a lot of inspections, understandably. So this is an option where you could just drop a detector at the site, collect data maybe remotely from that detector and ensure that the reactors are not operating or doing what they're supposed to do. I think this image was made by you, James. It gets, we've used it a lot. But I think it helps you imagine this. And I also, when I look at this image, I guess some of you are on double show, but on some level, all reactor sites look the same from the air. There's a big river and so you can imagine things like this happening there. In terms of the sensitivity, we base this on actual prospect measured efficiency and backgrounds with a prospect size detector. So you guys saw that's, it could definitely fit in a shipping container. You could verify that both of these reactors are off. You could see if they turned on within a day for the bigger reactor and 2 weeks for the smaller reactor. Maybe 2 weeks is not super impressive. It would be nice to get quicker notice. The limitation there is just the backgrounds. So again, if the technology can develop in such a way that the backgrounds are reduced, you could get a much faster, clear signal there. This is just looking at detecting turn-ons, but you can verify that it's operating on a civilian cycle and so on as well. Anyway, maybe the more kind of compelling part of that idea is that it could be part of something more like a cooperative threat reduction program for North Korea, where that verification exercise at the North Korean site could be paired with an observation of South Korean detectors. At least at this time, the South Korean administration was really interested in cooperative efforts and kind of things geared towards reunification. There would also be great regional partners for weapons scientists getting involved in bigger programs, which again just recalls how things happened with the Soviet Union. Actually, the SAGE experiment, which we hear about now because of its anomalous calibration result, it was a solar neutrino experiment, but they have the SAGE anomaly. It's the galaxy SAGE. You know what that stands for?
Yeah, Soviet American.
Yeah, Soviet American gallium experiment. And so it was one of these programs around the time of Nunn-Lugar that was bringing together Soviet and American scientists. And, they started while the Soviet Union was still together and it was opening up. And then it's interesting, the history of the experiment persisted even as so much political change happened. Now, was its overall impact on the political situation great? Probably not. But I think it's useful to think about these small things that could be part of a bigger program. And we managed at that time to, it was a group of us from kind of all the parties that had participated in past diplomacy with North Korea, like the 6-party talks countries and others. And we collaborate regularly with physicists there, and we try to get this idea out to people who are looking for different suggestions, sort of creative ideas for the diplomacy that seemed possible at that time. And interestingly, it actually did get some attention in South Korea, where, as I said, there was a lot of interest in cooperative proposals. I mean, presumably, this was not discussed at the highest levels, but this is a little video made by a South Korean state-sponsored English language news program, which showed up somewhere that we saw that there was kind of openness to proposal, even this sort of unusual. But as you know, that diplomatic window closed as abruptly as it opened, and there hasn't really been a chance to think about something like this in the meantime. However, there have been other developments worldwide that have got neutrino physicists thinking about possible applications. This is a very interesting one. So in September of 2021, the US, UK, and Australia entered this agreement, AUKUS agreement, in which the US and UK agreed to transfer submarine technology to Australia. And the US and UK submarines are fueled by highly enriched uranium, so presumably that's the type of submarine Australia would be getting. And this was kind of alarming to some non-proliferation experts, because up to now, all countries that have nuclear submarines, and particularly HEU-fueled ones, also have nuclear weapons. But Australia doesn't have nuclear weapons, so there's sort of a potential open for the HEU fuel to be diverted from the submarine into a weapon. Now, probably in the case of Australia, that's not, that much of a concern. But I think the concern in non-proliferation circles was that it kind of, sets a precedent for future transfers like this. There is in the NPT kind of a naval loophole where materials that are used for submarines they're not tracked by the safeguards regime. So the suggestion for neutrinos here was to verify that the nuclear material, the reactor core on a submarine, was still on the submarine at some future time. It hadn't been replaced with a diesel system, allowing that nuclear material to be used otherwise. And the reason neutrinos are kind of attractive here is because you can measure the neutrino signal from the reactor from, not a great standoff, but say tons of meters, without actually getting into the sensitive details of the submarine at all. And interestingly, as a technical matter, it doesn't even require the reactor to be on, because the reactor has to have run at some point in the past. But when it's shut down, there's enough residual neutrino emission from the reactor core to make a signal that, again, if you have low enough backgrounds, you could observe in, say, a few days while a submarine is in port. So it kind of fits in the envelope of operation that you could actually imagine for a submarine. So this really got the attention of the National Nuclear Security Administration and others. They'd be interested, I think, in getting the technology to the point where you could do this. Another thing that NNSA has been interested in recently is transparency of activities at the US nuclear test site in Nevada. Now, the US hasn't tested nuclear weapons since 1991, and there's not an announced plan to do so, but there are non-nuclear tests occurring, or activities occurring at the test site, and sort of uncertainty broadly, or accusations about what those might be. And so the NNSA is interested in activities that would allow other countries to be sure that what's happening at the US site is not a nuclear test. In fact, the NNSA administrator has kind of explicitly asked for ideas for future engagement directly with Russia and China in multilateral confidence building measures, like come to our test site, we'll come to yours. And this might be conceivably a place where the sort of short range neutrino experiment of the style originally envisioned but never carried out by Fred Linus could be put to use. And in this case, you're hoping not to detect neutrinos, since the absence of neutrinos would indicate the absence of fission. Of course, there are easier ways, just look at neutrons or other signals. But if you want to have kind of multiple lines of evidence, and I think particularly post a cooperative experiment with some scientific interest, possibly neutrinos are a nice fit for this, and NSA seems to at least want to explore this further. By the way, there's precedent for joint experiments at nuclear test sites. There was a series of nuclear tests in the 80s in which, there was exchange of weapons scientists between the US and Soviet Union to develop the seismic technology that made some of the test ban agreements at that time are feasible. So again, I mean, sometimes these things are hard to imagine, but there's actually cases where it was not. There are additional ideas for neutrinos. One I haven't mentioned is monitoring spent fuel. So it's sort of the same idea as with the submarine reactor. When it's off, there's still a residual neutrino emission. You could, for example, re-verify the contents of fuel storage casks. And some more of these possibilities are discussed in a report that NNSA commissioned a couple of years ago called New Tools. So this is a nice resource for further discussion of all these things. Anyway, let me just close with a brief look forward at what we're trying to do to develop technology that could work for that naval core verification case, or possibly be an option for the test site transparency concept, or even if there becomes an opportunity for something like a cooperative program in North Korea. So this is the mobile anti-neutrino demonstrator. So you've seen our collaboration now. And the goal here is to build a kind of ton scale or just below that detector, which would really be able to be transported to a reactor or other site and operate kind of on its own very stably for a long time without people there. So that really hasn't been done before with a neutrino detector like this. And it makes use of novel simulator materials, as we were talking about, with good background rejection capabilities. So this could be a whole talk in itself, but I'll just leave it to say that we're working to build this system. Again, James is one of the serious engineers involved in this. And this should be built and ready to deploy by like the end of this year. All right, so overall, I think there are a lot of possibilities here, some of them quite remote, but really some of them easier to imagine perhaps being useful in some niche cases. And hopefully soon we'll have the technology to really make that an option for the policymakers. All right, thank you. Got time if you have.
Few questions?
I'm not sure if there was any interest or discussions about maybe using something like this to monitor the sunk nuclear submarines to verify core integrity, like the Thresher or the Scorpion.
Right, so tell me more about what the.
Oh, like the Thresher went down in the 60s.
Okay, so
and
yeah.
it should not.
So maybe try to locate it or just
monitor, make sure the core integrity is good.
Core integrity. Yeah, I mean that's actually a little bit like the kind of reprocessing waste analysis is sort of like a nuclear forensics concept. And there have been looks at how that could work. It's difficult because the longer you wait after the reactor is off, the less neutrino signal you're getting. And so like there's been a nice study of at the North Korean nuclear site, could you look at the waste from past reprocessing and figure out exactly how much plutonium was made at different times? And maybe there's some like gross sensitivity to a factor like 2 in that case. So I'd imagine that, it's similarly limited if you're trying to look at an old reactor. We talked a lot before this, but.
Yeah, the one thing, North Koreans have a graphite reactor. You're going to almost comment on that, but graphite reactors were banned worldwide after Chernobyl. So that's indication of what a level of a rogue nation North Korea is.
Yeah, but I mean, it's old. It's from like that era.
Is it really? Okay.
Yeah, that one is.
Yeah.
Yeah, I mean, and they have a few other reactors actually. There's a smaller one at that site in But they actually seemingly have at least on an international scale, a record of pretty good nuclear safety.
Yeah, that's why I was just wondering about that.
Is space different? Like, could you detect stuff in space using this technology?
I think the difficulty would be that, once you even get into low Earth orbit, like what's the altitude there? It's a quite long distance. You're getting into that kind of worldwide reactor monitoring regime where you're going to need a big detector mass, which might not be amenable to, launching.
The backgrounds that you've been talking about for these detectors, mostly muons or something else?
So for like this system, the backgrounds are mostly cosmic ray neutrons. So it's the primary neutron component of the cosmic ray flux, which I didn't really think about. Underground experiments don't see that because it gets filtered out by, if you have any rock overburden, and then it's the secondary neutrons produced by muon interactions. But the primary neutrons are more significant here. Yeah, oh yeah.
Let me know if this is too beyond the scope, but I'm wondering if another window of opportunity opens up in terms of negotiations with North Korea, you have a sense of what might be the process of getting these sorts of neutrino technologies actually included in some sort of agreement or in some set of confidence building measures.
Yeah, I mean, we try to kind of understand more about this. And what I do know is that, for example, in the Iran nuclear deal, there were a few kind of more recently developed technologies implemented, some of the enrichment level verification monitors, I believe, were developed at Oak Ridge, not too long before that. And it kind of happened. I mean, it's things like the AAAS fellowship where people happen to have been in different offices and there's some kind of personal awareness of the technology. I don't know that there's otherwise a very centralized way that it will be asserted.
Thank you.
Thanks so much for your attention, hosting me here. And, yeah, I'd love to talk more, but I want to let you guys get going with your day too.
Thank you so much for having me speak.